Hello everyone, my name is Yuxi Luo. I'm a PhD candidate at Harbin Institute of Technology and a joint PhD student at the University of Toronto. The title of my report today is Large Edge Simulation Study on the Application of a Whisker Structure to the Lip of a Trailing Edge Cutback. I will present my research from the following aspects. Modern high thermal efficiency aero engines and gas turbines are designed to operate at extra high turbine inlet temperatures that far exceed the blade material's melting point. Consequently, the cooling system, including internal cooling and film cooling, are used to protect the blade from thermal ablation. For aerodynamic reasons, the trailing edge of turbine blades should be designed to be as thin as possible, resulting in tight design requirements for internal cooling space. Therefore, the trailing edge ejections, including central trailing edge ejection, pressure side cutback, and pressure side film holes, are utilized to cool the trailing edge. For the trailing edge cutback cooling, coolant flows out of the cooling channel to cover the cutback surface and protect the cutback surface from ablation. Vorticities shading from the lip will intensify the mixing of hot gas and coolant, thus reduce the film cooling effectiveness of the cutback surface. A finding showed that reducing lip thickness can improve film cooling effectiveness, but it will weaken the strength of the blade's trailing edge. Therefore, it is necessary to find some structure to suppress the vortex shading from the lip while maintaining sufficient trailing edge strength. Blend harbor seals and harbor seals in turbid waters can track prey with unique whisker structure. In uniform incoming flow, the structure of the whisker can suppress vortex-induced vibration to reduce the noise of sensing, while in the upstream wake, the whiskers are able to generate a unique vibration. Hank showed that the harbor seal whisker broke the coherent structure of the common vortex, thus suppressing vortex-induced vibration. In previous studies, we applied the whisker structure of the harbor seal to the turbine blade trailing edge. The whisker trailing edge can suppress the vortex shading of the trailing edge and reduce aerodynamic loss and reduce the interaction between the valence wake and the blade. And today I will introduce the application of the harbor seal whisker structure on the lip of the trailing edge cutback cooling. The computational domain is shown on the left. The main flow is hot gas and the coolant flows out of the cooling passage to cover the cutback surface. The generation method of the whisker lip is shown on the right. The elliptic lip is determined by the ratio of the length of the major and minor axis being 2:1. For the whisker lip, the geometry before the cut-off point remains the same as the prototype. The control points 1 and 3 are the minor and major axis endpoints of the ellipse, which vary sinusoidally in the lateral direction. Only the control point 2 of the case 1 varies along the lateral directions. The amplitude of the sinusoid at control point 1 gradually increases from case 2 to case 4. Third-order Bezier curves are used to connect the cutoff point and the control point, and the elliptic curve are used to connect the control points. A comparison of the lip geometry is shown on the left. A total of 6.47 million gray cells are used to discretize the computational domain. LES with warm adapting local ideal viscosity was used to simulate the flow and heat transfer process. The laterally averaged film cooling effectiveness obtained from the large AD simulation is in good agreement with the experiment. Compared with the DS method, the results of the LES are more consistent with the experiments. Okay, the results and discussion. The laterally averaged film cooling effectiveness of the cutback surface shows that the elliptic lip and the Whisker lip can improve the film cooling effectiveness of the cutback surface to different degrees. Especially Whisker K3 achieves the best results at the median bloom ratios from 0.7 to 0.9. The contours of the adiabatic film cooling effectiveness show that the distribution of the film cooling effectiveness of the Whisker lip is not uniform in the lateral direction at median and low bloom ratios. The film cooling effectiveness corresponding to section B is higher than that of section A. The ISO surface of Q criterion shows that the shading vortex of the prototype lip is surprised by the elliptic lip and the Whisker lip. Hairpin vortices appear in the shear layer of the elliptic lip. The temperature contours of different cross-section show that for the elliptic lip, the mixing of the shear layer begins to intensify at the middle of the cutback surface. The shear layer mixing of the Whisker lip corresponding to section A is stronger than that of section B. The cooling coverage effect of section B is stronger than that of the section A, especially for K3. The boundary layer is analyzed to reveal the cause of the uneven distribution of the film cooling effectiveness on the cutback surface in the lateral direction. Section A and section B correspond to the valley and peak of control point 1, respectively. Warm streamlines show that the boundary layer of the Whisker lip presents a distinct three-dimensional separation pattern. The boundary layer of the Whisker lip converges from the peak to the valley before separation. The boundary layer velocity profile is measured at the peak and valley of control point 1. This convergence makes the boundary layer thicker at the valley and then at the peak. As the amplitude of the sinusoid at control point 1 increases, the thickness of the boundary layer increases at the valley and decreases at the peak. The vorticity contours of different cross-sections are shown in the figure. Thicker boundary layer in section A enhances mixing, and a thinner boundary layer allows for a better coolant coverage in section B. Okay, the conclusion. The elliptic lip and the Whisker lip can improve the film cooling effectiveness of the cutback surface to different degrees. K3 achieves better results in median blow ratios from 0.7 to 0.9. The boundary layer of the Whisker lip converges from the peak to the valley before separation. As the amplitude of the sinusoid at control point 1 increases, the thickness of the boundary layer increases at the valley and decreases at the peak. Thicker boundary layer in section A enhances mixing and decreases the film cooling effectiveness. Thinner boundary layer allows for a better coolant coverage in section B. Thank you for listening.